Hi, my name is Holly Mesrobian, and I'm the director of AWS Lambda. Soon, I will be joined by Marc Brooker, senior principal engineer for Serverless. In this talk, we will go over some of the underlying systems that makes AWS Lambda work. Last year, we spoke about the systems and flows involved in the sync invoke path and a new micro VM technology Lambda was built on called Firecracker. This year, I will cover a brief introduction and summary to set context for those that didn't attend our talk last year. We will then switch over and provide a lot of new content. So, if you attended this talk last year, stay put for the first 5 or 10 minutes, and if you didn't, I will try to catch you up to speed before we go into a lot of new information. First, a little bit about Lambda so you understand the scale of what we're doing. AWS Lambda already processes trillions of requests across hundreds of thousands of active customers every month. Lambda is currently in 22 AWS regions, and as a foundational service, we launch in every new region that AWS launches. Lambda integrates with 47 AWS services, making it easy to get up and running quickly. We have a number of customers that are using Lambda to build highly available, scalable, and secure services, including Thomson Reuters, who processes 4,000 requests per second for its Products Insights Analytics platform, FINRA, who performs 500 billion validations of stock trades daily for fraud and anomaly detection, and Zillow, who uses Lambda and Kinesis to track a subset of mobile metrics in real time. Now, let's turn to why so many customers are adopting Lambda. And it's because running highly available, large-scale systems is a lot of work. First, you need to ensure that your system has load balancing at every layer of your architecture. You do this so you have redundancy in your architecture, but also so that you can handle more traffic than a single server is able to serve. When you plan to build a new service, you need to plan for and provision for these load balancing layers between primary architectural components. You also need to ensure you have these systems configured with appropriate routing rules such that your load is distributed evenly. Second, on the point of more than a single server can serve, you need to support scaling up, so if you have more traffic than your current service layer can handle, you can continue to serve that traffic. But you also need to be able to scale back down after traffic peaks so that you're not indefinitely over-provisioned. When you plan to build a new service, you also need to plan for and provision these auto-scaling layers to sit in front of your fleet, evaluate the capacity of the fleet, and scale up with traffic volume and stress on your server pool and down when peak traffic decreases. Third, continuing on the point of system failure. You need to consider both when a host fails, but what about a complete failure of a data center or an availability zone? To this, you need to instrument each of your services with health checks based on key service metrics. And if the service shows as unhealthy, stop routing traffic to that host. And fourth, in distributed systems where you have many components and network routes in play, predictable latency is hard to achieve. And as an engineer, you must continually focus on driving down outlier latency. These are your 2, 3, 4 nines and beyond. Then you need to repeat to ensure you do this for every single system and service component that you build. As a developer, you're now spending a lot of your engineering hours on systems administration. Lambda takes care of all this for you and more, helping developers to focus on business logic by writing code and not administering systems. Today, we will show you how Lambda transparently supports event and stream processing for big data workloads, managing load balancing, scaling, and error handling. We will also cover how we've architected Lambda around recent improvements to manage predictable performance with a feature called provision concurrency. And finally, continuing on from last year's discussion on Firecracker, we will provide some updates around isolation. This is a lot to cover, so let's get started. As you may recall from last year, the Lambda service is split into the control plane and the data plane. The control plane is where you as a developer interact with Lambda. This is where you upload and configure your code in preparation for execution. The data plane is where your customers interact with Lambda. It is what triggers your code to execute. Today, we will again focus on the data plane. Last year, we covered the synchronous invoke path on the data plane, and as promised, we had plenty to talk about. For those of you that haven't seen the talk from last year, I will quickly provide the Cliff Notes version on the sync path. This year, I want to cover what I hand-waved over last year, the async event and streaming invoke path architecture. As you may also recall from last year, the sync invoke path is eventually executed for both event and stream-based use cases, and so it's good for you to have a basic understanding of how these systems work. So let's start with the synchronous first-time invoke or scale-up. This is what we commonly call a cold start. And what happens here is the Lambda customer calls invoke, which hits an application load balancer, and the application load balancer routes to a front end. The front end's responsibility is to authenticate the caller, make sure that that caller has the permissions to invoke the function, and then check function metadata and confirm that the per function concurrency hasn't been exceeded. Assuming that all looks good, then the front end routes to the worker manager. And the worker manager's responsibility is to track warm sandboxes that are ready for invocation. And since this is a first-time invoke or scale-up, there is not a sandbox that's there and readily available, so the worker manager needs to communicate with the placement service. The placement service's responsibility is to find the best location on a given host to place that workload. And so placement does that, provisions that sandbox and returns it back to the worker manager. At this point, the worker manager can call init, and that initializes your function for execution. It then returns to the front end, which calls invoke. Continuing on from here, on a sync invoke on a repeat, this is what we commonly call a warm start, and this is where the vast majority of Lambda invocations land. The customer again calls invoke, which hits an application load balancer, which is then routed to the front end. The front end again authenticates the caller, checks function metadata, confirms that the per function concurrency hasn't been breached, and then the front end routes to the worker manager. This time, the worker manager knows that it has a readily available sandbox that can take that invoke, and so it gets that, returns it to the front end, and the front end can call invoke, and that again executes your function. And so you can see that's a much shorter path of execution. So turning back to the async invoke path, it has several components, including pollers, state manager, stream tracker, and leasing service. Let's talk about each of these so you have an understanding of what components' responsibilities are. The poller is responsible for consuming events and ensuring that they are processed. For event sources, it consumes events from queues, either customer-owned, as in SQS as an event source, or Lambda-owned, as in async. It retrieves function event destination configuration data, triggers a sync invoke with the requisite payload, manages retries in case of failure, checkpoints in a heartbeat, and delivers the completion data for the function to an event destination. For streaming sources, it subscribes to shards, monitors changes to function name, metadata, or batch size, and updates its local state, invokes the Lambda function as soon as any data is received, supports batching rules, invoking the Lambda function for a batch size of data or a batch time. If it's throttles, it backs off and retries. It checkpoints in a heartbeat, updates the streaming source with reason code when it receives an unrecoverable exception, and drops its assignment when the streaming source is disabled or deleted. The state manager, or stream tracker, is responsible for handling scaling by managing pollers and event or stream source resources. For event sources, it's the state manager. It creates new static queues as it scales up with load for large per-function concurrency. It creates or updates the desired number of polling assignments in the leasing service, monitors creating, updating, and transitioning states driving to the desired state for the event source, and creates dwell time or assignment level metrics used as an indicator of system-wide performance. For streaming sources, it's the stream tracker. It exposes an API to manage streaming sources, calls list shards and creates leases with the leasing service for each of the shards, checks periodically for function updates and other streaming source updates which require changes on leases, scans for streaming sources, checking for any streaming source when a lease has not been created, exposes an API to sync a shard when the poller has reached shard end, and disables the streaming source when all the shards have reached shard end. The leasing service is responsible for assigning pollers to work on a specific event or streaming source. For event sources, it manages poller assignments as specified by the state manager. It maps pollers to queues, decides the number of pollers per queue to process events, handles acquiring and releasing poller assignments, and checks periodically assignment health and makes unhealthy assignments available to new pollers. For streaming sources, it scans and provides assignments to pollers, exposes an API which the stream tracker uses to manage giving and releasing assignments on pollers, and acquires the shards after their parents have been executed up to shard end. Many of you are using the async invoke path as you process your workloads. For instance, you are using the path when you either call our invoke API asynchronously or when you hook up an event source such as SQS, SNS, S3, or AWS events to Lambda. Serverless customers which are doing high-scale event processing include Siemens, who have built a solution using SQS, and CSIRO, who use SNS in their genome search engine. And here's a quote on how easy serverless is. So, how is an async invoke processed? Let's walk through this. The Lambda customer calls invoke asynchronously. This calls the front end. The front end places a message on a queue. There's a set of pollers assigned to that queue. The assigned poller pulls the message from the queue and processes this message by placing the message on the front end synchronously. From there, it follows the sync invoke path, which we just covered. So how is this different for event sources such as SQS as an event source? Well, it's not very different. You are providing the connection to the event source, whether it's your SQS queue or one of the other event sources Lambda supports, and Lambda does the rest. So that you can receive information from an async call, we have launched something new this year, which is invoked on this path, called Event Destinations. Event Destinations provides customers visibility into results from an async invocation and provides us visibility for a number of event sources, including SQS, SNS, AWS events, and async Lambda. So how is an event destination processed? Let me show you. The customer again calls invoke asynchronously. This calls the front end places a message on the queue. There's a set of pollers assigned to that queue, and the assigned pollers pulls the message from the queue and processes the message by placing the message on the front end synchronously. The sync invoke is processed. Whether the event is processed successfully or fails, in addition to deleting the message from the queue, the response is delivered to the event destination. So how does the system scale up and down with load? Well, this is where the state manager and leasing service come in. As we discussed earlier, the state manager is responsible for scaling up queues and associated pollers to keep up with processing the incoming events up to the per-function concurrency configuration. And leasing service is responsible for acquiring and releasing assignments to pollers. Let's walk through this. The state manager discovers work on the queue. The state manager reads the change and will create the poller's assignment with the leasing service if there's a large per-function concurrency setting. The state manager will create a new dedicated queue. And if a small per-function concurrency, the state manager will use an existing queue. The state manager ensures there is poller redundancy by assigning multiple pollers to a given resource. The pollers read their assignment from the poller assignment data. So how does the system handle errors? Again, the leasing service comes in. As we discussed earlier, the leasing service is responsible for periodically checking assignment health and making unhealthy assignments available to pollers and detecting assignments that have not been heartbeated and giving that assignment to a new poller. Let's see how this is done. There is a poller that is assigned to process an event source. The poller stops processing its assignment. The leasing service checks assignment health and sees an assignment that hasn't been heartbeated in the expected period. The leasing service makes a new assignment, making the unhealthy assignment available. Another poller picks up the assignment and starts processing the event source. We are also launching something new this year called retry policies. In the past, we handled errors with static retry policies, which determine the number of retries we would perform and for how long. With retry policies, we are enabling customers who wish to proceed with processing incoming events to set their function's maximum age so as to tell Lambda to skip any invocations older than the configured number of seconds and instead resume processing newer invocations. The maximum event age can be between 60 seconds and 6 hours, providing a lot of flexibility for your use case. Customers who've backed up their queues with unwanted invocations can also set this max age to the lowest configurable value, causing Lambda to delete, or DLQ, all backlogged invocations. Customers who want to control the number of attempts made to execute their function can set retries to 0, 1, or 2 attempts. So how is an event processed when there are failures? The Lambda customer calls invoke asynchronously. This calls the front end. The front end places a message on the queue. There's a set of pollers assigned to that queue. We're getting familiar with this process. The assigned poller pulls the message from the queue and processes this message by placing the message on the front end synchronously. However, an error is returned from the front end due to a failure condition. The poller will observe the retry policies and will wait and retry again. Let's say in this instance, we had configured for 1 retry and had a DLQ configured. On the retry, there is still an issue with the invoke, and the retry fails a second time. At this point, the message is placed on a queue of failed invokes, and the message is deleted from the queue. Many of you are also using the streaming invoke path as you process your workloads. For instance, you're using the streaming invoke path when you hook up your Lambdas to DynamoDB or Kinesis. Serverless customers which are doing high-scale stream processing include Blissfully, who has a serverless parsing flow that leverages Kinesis streams. So how are streaming events like Kinesis and DynamoDB processed? Your application places 1 or more records onto Kinesis. The assigned pollers receive the message from Kinesis and processes the messages by placing the messages onto the front end synchronously. Similar to what we already covered, the sync invoke path is then used to process the event. So how are streaming events like Kinesis and DynamoDB established? Similar to events, pollers are mapped to streaming sources. Stream Tracker, like State Manager, reads changes on shard mappings. The Stream Tracker then uses the leasing service to manage leases of streams. The pollers read their assignments. The pollers then subscribe to shards for Kinesis. So how are streaming events like Kinesis and DynamoDB scaled up and down? When a stream is enabled, we look at the number of active shards to determine the number of pollers. If a stream has in shards, we create 1 poller assignment. For every in shards, we add another poller. When Kinesis adds an additional shard, the Stream Tracker triggers logic to calculate the concurrency required to process the stream. If additional shards are added, then the Stream Tracker creates additional concurrency with the leasing service based on the number of additional shards. The number of shards are assigned evenly across the pollers. The pollers have many threads to pull concurrently from the shards. To help with supporting large-scale stream processing, we are now supporting parallelization factor. For streaming event sources with high-volume streaming events, the shards will fan out processing, increasing Lambda parallelization while preserving ordering guarantees per partition key. Okay, thank you. Customers are able to provide a parallelization factor, and pollers scale up the parallel processing by that factor for each shard. Let's walk through scaling up and down. The Stream Tracker detects by calling list shards that there is a change in the number of shards requiring a scale up or down. In response to this, the stream tracker adjusts the number of leases with the leasing service. The pollers retrieve their new assignment with the desired number of pollers required to process the shard volume. The poller then subscribes to the shards. So how are streaming events like Kinesis and DynamoDB resilient to failure? We support exponential backoff and DLQ support. Lambda processes streaming event sources with in-order guarantees, and failed batches are retried until the records in the batch expire. We allow customers to specify a max number of retry attempts, record expiry time, and a bisect batch on failure parameter to allow retries with a smaller number of records. When the Kinesis shard throughput exceeds the Lambda per function concurrency, then throttles occur with exponential backoff. Information about skipped records will be sent to a destination specified by the customer. The supported destinations are SQS and SNS. Let's walk through how error handling with a retry, a batch bisect on retry, and a DLQ works. Your application places one or more records onto Kinesis. The assigned poller receives the message from Kinesis and processes the messages by placing the messages on the front end synchronously. The front end fails to process the batch provided the first time. The poller splits the batch in two and retries with two batches. This time, one batch succeeds and the other fails. The poller writes the failed batch info to the configured DLQ. Now, I will turn things over to Marc, who will cover how we've built predictable performance in Lambda.
Great, thanks, Holly. It was very slippery outside yesterday, and I managed to bang out my knee, so you see me hobbling around the stage. Please forgive me. Hi, I'm Marc Brooker. I'm a senior principal engineer with the AWS Serverless team. And before Serverless, I worked on Lambda, EBS, EC2, IoT, and a couple of other pieces around AWS. And today, I'm going to be talking about a couple of kind of internal topics. And the first one is Lambda provisioned concurrency. This was a feature that we announced on Monday. And the short version is, hopefully everyone in this room has seen this, but if you haven't, please go and check out the documentation. But the short version is that turning on provisioned concurrency lets you keep your functions initialized and ready to respond within milliseconds. So one of the things we heard a lot from Lambda customers over the years is, really like Lambda, like the P50 performance because of warm start. But when those cold starts happen, and especially cold starts with big code bases, Java, whatever, those can be, break people's expectations of latency, which is very reasonable. We all have customers waiting on the responses to our services, and this is where hyper-ready is super useful. You can turn on provision concurrency. You can turn on provision concurrency and say, well, I want 400 concurrency or whatever, and you can also set that up with auto scaling, and we will make sure that you don't get those cold starts. And I want to talk about how we designed provisioned concurrency. Because it might not be, be obvious why these were the right choices. And I'm going to do that by stepping into each of these words and starting with the word concurrency. One of the things I'm really excited about with provisioned concurrency is that I think it is by far the easiest way to build latency-sensitive interactive services in the cloud. And part of the reason for that is this idea of concurrency. In my mind, concurrency is the right way of measuring service scale. So let me explain why. Why not provisioned capacity, right? Why not say, hey, Lambda, provision me 5 hosts or 10 machines or 300 cores or 5, whatever. That's for 3 reasons. One of them is that with capacity, performance depends on hardware. The amount of capacity that you need for any given workload depends on the performance of the hardware. So if you buy new CPUs, you buy faster memory, anything changes about the platform, changes about how fast the network is, the amount of hardware you're going to need changes. And being able to get this right and choose the right amount of capacity to buy requires a deep understanding of hardware performance. And so, we didn't expect that serverless customers need to have a deep understanding of hardware performance because we believe that serverless customers, that is one of the values that we provide with serverless. Whereas concurrency is just a measure of work. It's not a measure of capacity and therefore doesn't depend in the same way on hardware performance. A capacity model would need to model host and AZ failure. And as we all know, hosts fail, networks fail, power fails, and very rarely availability zones fail. And we invest very deeply at AWS in making these things fail as seldom as possible, as infrequently as possible. But it is very important in a high availability architecture to design things in a way that there is enough capacity when these kind of AZ scale failures happen. And so in a capacity model, you would have to reason about that. Whereas in a concurrency model, and in Lambda provision concurrency, that's built into the product. We handle that for you. When there are host failures, when there are infrastructure failures, when there are AZ failures, those are things that we will detect and react to, and you don't have to carry extra capacity or extra concurrency to deal with those failure cases. It's built right in. Another issue with capacity is that changes in your business logic can affect how efficiently you use capacity. And this is particularly an issue in cases where folks have, a development team or some teams working on business logic, right? Like working on features for your customers, and a separate team or a separate group working on capacity management. And if these two teams aren't talking to each other very, very closely, what can happen is the business logic folks are going to add more features, as is their job, and that's a fantastic thing. But the expectations of the amount of throughput you get out of capacity will sort of drift over time. So then why not provisioned rate? Why not provisioned TPS? And this is another kind of factor that people tend to consider as a key factor in the scale of systems. So requests per second. First, it doesn't consider work per unit. A lot of things like Lambda streaming integration, if you use DynamoDB or Kinesis, we're going to create batches for you. A couple of knobs around that. And if you're measuring requests a second, you aren't measuring the effects of batching. So what's going to happen is 100 requests a second of size 1 batches is a very different amount of work from 100 requests a second of size 100 batches. So requests per second is a pretty poor measurement of work done as soon as you start doing any batching. The other problem with requests per second is also per unit of work done as long as you have any heterogeneity in what your APIs do. So the example here is you have a list API, which says, get me all of my things. And that can be thousands of things, or hundreds of thousands of things, or millions of things. Show me everything I've bought, on Amazon.com in the last 5 years. And so that can be a very expensive thing to implement, whereas a get API typically is a get by primary key. Go get me that thing. And that's typically way cheaper. And so if you're measuring, requests per second of 1, it's going to mean a very different thing for the amount of scale of your system from requests per second of the other. Whereas concurrency, because concurrency kind of multiplies out requests per second and latency, or amount of work that needs to be done, this is built in. It's considered. And finally, requests per second doesn't consider the effects of contention. And I'm going to dive deep into this because this is actually quite a subtle point, and it's something for me that's very important about serverless and one of the advantages that serverless offers for building high-scale systems. So we're going to have a couple of these graphs. On the x-axis, we have work offered. This is the amount of work kind of coming into the system, saying, this is, and here I'm measuring that in concurrency units. So the amount of work offered increases, more traffic comes into the system, and in an ideal kind of naive world, perfectly stateless system, no coordination needed, the system scales perfectly, and work completed goes up just perfectly linearly with work done. And you can build stateless systems like this. And in fact, if you build a simple stateless Lambda function, this is what you're going to get. You're going to get, Lambda scaling up and your system scaling up as more work is offered. But most kinds of systems that we build, most distributed systems, have some contention points in them. Right? They have some shared shared database rows, shared work items, shared queues, and so on. And that introduces contention into the system. And contention tends to slow our systems down. So let's talk about two sort of models of that. There's the classic, which is Amdahl's law. And Amdahl's law says, there's an amount of available concurrency, amount of available parallelism in the system, and an amount of kind of serious time spent on serial work. And as you go up, the serial work starts to dominate, and your throughput sort of levels off. So all of us have been to kind of lunch in the reinvented halls, and they've done a fantastic job of feeding a huge crowd of people and feeding with a lot of concurrency. Right? There are a lot of these tables serving food. You go into the hall at the Venetian, and there are probably 25 lines of buffet tables. But at the entrance of the hall, there's a single door where they're checking your badge as you go through. So here's your mental model of Amdahl's law, right? Like everybody has to go through that door, and then you can fan out and you can go through all of those buffet tables in parallel. And so if they added more and more and more and more and more lunch tables, eventually that door would become the bottleneck, and your throughput would be limited to the number of people you can get through the door. So that's the kind of contention making things stop scaling effect. But there's something even worse that happens under contention in distributed systems, and that is, the chaos of things coming and going actually tends to make performance drop. Amdahl's law is wildly optimistic because it is assuming that the amount of throughput you get through these serial things, through that door, is constant no matter how many people are trying to fit through. So if everybody queues up perfectly and walks through a door kind of nicely serially, that'll be true, right? There's no contention. But if people came from every angle and tried to crush through a door, there's way less throughput, right? So you can see there's some number of people kind of arriving at lunch from different angles that will reduce the throughput at the door. And eventually you get to a point where there are just people like clambering over others and so on, and there's no throughput through the bottlenecks in the system. And this happens in real distributed systems too. And it happens because of contention. And that can be contention on locks, it can be contention on shared resources, it can be contention on shared database rows in poorly designed schemas, it can be contention on garbage collection, and all sorts of things. And that varies based on your system architecture. But almost every system architecture has some point where it tips over like this. And probably the most famous one for distributed systems folks is Paxos. Obviously Paxos is one of the classic distributed systems algorithms, and it's got this really nasty edge case where as the concurrency or attempted concurrency goes up, it suffers from what's called live lock, and essentially throughput drops off to zero. And exactly the same thing happens in a lot of kinds of distributed protocols and is very hard to manage. So almost all real systems have some point, right? Some point that they're going to start collapsing under contention. And that could be when they saturate their NICs and start getting packet loss. It could be when they saturate their storage devices and start slowing down under their logging or metrics load, and so on. There's always some point. So this curve might be, that might be way over on the right-hand side. And if you're using a scalable cloud service, it will be way over on the right-hand side. But eventually that's going to happen. There's eventually a point where systems collapse under contention with more offered load. And so there's a sweet spot of just the amount of work offered which maximizes the throughput of a system. And one of the cool things you can do with the combination of Lambda per function concurrency and Lambda provisioned concurrency is you can benchmark the bottlenecks in your system, whether that's a database or an old legacy service or a SaaS application, find the point of maximum throughput, and use those features to dial in your Lambdas to keep your system at that sweet spot and provide back pressure in a very, very scalable way. We're really great at telling clients to go away. That maximizes the throughput of your system. So it's a very powerful set of tools and much easier to do on Lambda than it is to do with traditional infrastructure. And so why is it easier? Well, because with traditional infrastructure, you also need to make sure that your own infrastructure is good enough at telling things to go, telling excess load to go away, doing the back pressure, doing the throttling, and so on. Whereas with Lambda, because it's a shared service, and you tend to be, for a lot of your applications, a relatively small part of our scale, we can push that catastrophe so far out that you don't need to worry about it. So I wanted to talk a little bit about what's called Little's Law. And Little's Law is a pretty, maybe somewhat obvious statement about the work that systems do. And one statement of Little's Law is that concurrency the long-term average concurrency is equal to the arrival rate, the amount of stuff coming into the system measured in events per second, times the long-term average latency. And this is actually, it seems really obvious, but it's actually quite a deep statement because it turns out that Little's Law works no matter what the shape of the distribution is, no matter what the shape of the arrival rate distribution is and latency distribution, and so on. And one of the things that's hidden in Little's Law is an explanation for part of the reason it's so hard to build using traditional architectures, really great scalable, low latency distributed systems. And that's because latency tends to depend on concurrency, right? Because of those contention factors. So concurrency goes up because of more offered load, which increases latency, which increases concurrency because there's a multiplication factor, which increases latency, which increases concurrency, and so on. So you can see there's kind of a feedback loop that's built into systems that makes them kind of inherently unstable. And again, with the combination of per-function concurrency and provisioned concurrency on Lambda, you can avoid getting into this situation. So let's talk a little bit about the word provisioned much more quickly. So if you look at the amount of load on a server, exactly the same thing happens. You load your server, and there's some point, things go up nice and linearly, and eventually things fall off the end. And the way that looks, if you look at that in latency, is load comes in, and as I was saying, as you get to some point in more load, you get more contention, and the latency on your server goes way, way up. And so you want to keep all your servers busy and optimally busy and optimize your costs. You want to operate systems at that sweet spot. But that sweet spot's pretty close to a tipping point, so you've got to be careful. And what happens if you exceed that sweet spot? Well, you can do one of two things. There are pretty much only two things you can do. You can reject load. You can tell your customers to go away, which is a nice operational practice, but not a great business practice. Or you can scale up. You can add more servers, you can add more load balancers, you can add more network, and so on. So, scaling up takes time. Milliseconds to seconds on Lambda, depending on what your code's doing on the cold start path. Seconds to minutes on containers and servers, and who knows in your data center. Could be anything from seconds to weeks to months. Things like AWS autoscaling are fantastic and powerful, but they're also approximate because they have to work by proxy metrics like CPU, whereas Lambda scale-up can work directly on concurrency, which is in some ways, as I was saying earlier, the base metric of system scale. And the other thing that makes autoscaling difficult is that predicting the future, as we all know, is difficult. Why would you reject load? Well, again, traditional infrastructure tends to reject load by proxy. And by this, what I mean is that you benchmark your system and you pick something like requests per second, that you're going to say, well, don't exceed this, and start rejecting load as you get over those things. But that becomes really subtle when you have a heterogeneous mix of work coming in. You have different batching units and so on. So it's hard to do perfectly right. Whereas Lambda does this directly on concurrency. And concurrency, again, is the best measure of load on a system. And it does this with per function concurrency limits. So building, great low latency scalable web services, in my mind, requires, three things. There are sort of three horsemen of great low latency web service. One of them is the ability to control load. And this is, making sure that you don't go over that tipping point with whatever the congestion point is in your system. One of them is the ability to scale fast, because if you want to be near that sweet spot, which you do because that's going to help you control your costs, you want to, as soon as things start going near that tipping point, you want to be able to scale up and add capacity. And finally, you want to be able to provision ahead because the scale up might take longer than you're willing to accept as in a latency sensitive service. And so control load, this has been available for Lambda for more than a year. Scale fast, that's really sort of fundamentally built into Lambda, fundamentally built into our model of serverless, and provision ahead is available now. And so what does this all mean? Well, what it means is, as load on the system goes up, you hit your provision, and with traditional architecture, you'll go over that latency tipping point. And obviously, you'll eventually recover if your auto-scaling or your ops team kicks in and adds more capacity. With Lambda provision concurrency, instead, you'll step into a much nicer mode where you start cold starting again. Your latency jumps up, but it doesn't have this same catastrophe. I'm going to move on to talking about Lambda isolation under the covers. Those of you who listened to the keynote this morning would have seen Claire and Werner talk about Firecracker. And we spoke about Firecracker in context of Lambda last year. Firecracker is our open source virtual machine monitor. It's a component of virtualization that we built over the last few years. We've open sourced it. It's on GitHub. And as part of that project, we've been taking parts of, sorry, I didn't step forward there. We've been taking parts of Firecracker. We've been moving them out into a new project called Rust VMM, and to provide not only Firecracker as an open source project, but also Rust VMM as a set of crates, which, if you don't know Rust, are just libraries that folks can use to build their own VMMs. And Intel have picked that up to build Cloud Hypervisor, and there's a lot of interest from across the industry in this toolkit of VMMs. And so Firecracker provides the isolation between Lambda functions on the same hardware. So why do we have to do that? Well, we have to do that because, as you imagine, you run a 128 megabyte Lambda function. That's not going to run on its own server. That would be completely uneconomical. A modern server has hundreds of gigabytes of memory. So we run many different workloads on the same server, and we do that by cutting that server up using virtualization. So this is what it looks like. At the top of the stack is your workload. This is your code that you bring to Lambda, the stuff that goes in your function, goes in your layers, and so on. There's the Lambda runtime, either the one you bring or one of our built-in runtimes, like Java, Node.js, Python, and so on. And then there's a guest kernel, and this is literally the Linux kernel. It's a very minified Linux kernel where you take out the vast majority of kernel features, and Firecracker. And so all of the stuff in gray is dedicated to each individual Lambda function. You get your own runtime, your own guest kernel, your own Firecracker process, your own function code, and you don't see any of this stuff, but this is all stuff that we dedicate to you. And we're able to do this because these Firecracker processes are so lightweight. And so Firecracker provides the security boundary and the isolation by working with KVM, which is a feature of the Linux kernel. So let's step into that for a second. What does KVM do? Well, KVM's job in our stack is to tell the hardware, and these are features in Intel or AMD or ARM CPUs that provide virtualization. KVM's job is to program that hardware and say, here is a memory space, here's a set of page tables, here's some ways to handle page faults, and when a VM is just executing normal CPU instructions, don't get in its way. But as soon as it does something strange like page fault, tell me, and I'm going to react to that. So it sets up all of the stuff, memory management and paging and page tables and all of the stuff that you might know or you might sort of vaguely remember from your OS class, and sets those up completely separately for each one of the virtual machines. And it also provides some abstraction for us of hardware details. Every CPU manufacturer has their own hardware virtualization feature set. They are conceptually compatible, but not compatible at all in the actual details. And so KVM, which is this feature built into the standard Linux kernel, provides a standard set of controls for programming abstracted across all of these different types of hardware. So what is Firecracker's job then, if KVM is programming the virtualization? Firecracker's job is to configure KVM. This is the first and possibly most important thing it does, is it uses those KVM APIs to say, create me one of these virtual machines and boot this operating system in it. The next thing it does is provide device emulation, right? So we in Lambda can run hundreds to thousands of functions on the same piece of hardware. But we don't have a big box with hundreds of thousands or thousands of network cards, or hundreds or thousands of hard drives, or hundreds or thousands of serial devices. So Firecracker pretends to be hardware to the VM and abstracts the host hardware and cuts it up, multi-tenants it, and presents it as devices. I'll talk about that more in a second. It provides performance isolation, making sure that every VM doesn't take more than its share of any of the bottleneck stuff in the system. And this includes memory, storage, CPU, memory bandwidth, cache, and all kinds of other things. And Firecracker, as I said, is optimized for serverless. We built it especially for serverless, very low overhead, 5 to 8 megabytes, depending on what you're booting. Can boot Linux in 100-ish milliseconds. Can boot a microkernel in 5-ish milliseconds. And so it's very, very fast-moving, small piece of software. And so this is what the device virtualization looks like in detail. Firecracker sits there inside the host OS. Every Firecracker for every function is a separate process in the host OS. And it shares a little bit of memory with each virtual machine. And over that shared memory, they talk a protocol called VirtIO. And VirtIO, combined with a set of drivers inside the guest kernel, pretends to the guest operating system to be a network card, to be a hard drive, to be a serial device, or whatever else the kernel needs to boot. And so, they do this through shared memory, through a set of kind of ring buffers in memory. So, for example, your application inside Lambda does a write that will go into the guest OS. The guest OS will then decide it wants to commit it to disk, which will hand it to the VirtIO driver. The VirtIO driver will put it into the shared memory area, into the ring buffer. Firecracker will wake up, pull that off, and submit that to the physical disk, and then the acknowledgements will obviously flow up the other way. And so that's Firecracker sits on that I/O path. And if you listen to Werner this morning about Nitro and some of the other stuff we've talked about, Nitro at reInvent, with Nitro, with EC2, we do a lot more of that in hardware. Whereas Firecracker, because of the density that we need, there's a lot of more software on that I/O path, but very carefully optimized software. The other thing we do there for Firecracker is we take each of those Firecracker processes and we wrap that in a very, very restrictive sandbox. So, there's the hypervisor, hardware virtualization provided by the CPU that isolates your function code. And then we take the Firecracker process, which most of it, what it does in the active state is device emulation, and we wrap it with C groups and Chroot and seccomp and all of these other great kind of container security practices to create yet another layer of security isolation. So there's a real kind of defense in depth strategy there. So this is what it looks like in your stack diagram. Virtualization provides the really strong isolation, and the jailer, which is this component which wraps the firecracker, provides an extra level of control and virtualization. And one of the nice things about open sourcing Firecracker is you all can go on GitHub if you're interested, go to the Firecracker project, and we've got documentation that describes how this jailer works, and you can dive into the code and see exactly the way that we're wrapping this stuff up. And so it's something I'm very excited about, and very excited to have that kind of level of transparency with all of you, because we know that you are just as concerned, just as excited about security as we are. We all see it as job number one, protecting our customers' data. And so we wanted to share in detail how we did those things. So Holly talked about the high-level pieces behind Lambda, about that sync invoke path, about how the async invoke path works, about how streaming works and how things flow through the system. I talked about a provision concurrency and why I think concurrency is the right way to measure system scale, because it's a very basic measure of the performance of real-world systems. Why provisioning is a great way or great tool in your toolbox for building services with very predictable latency. And finally, I talked about Firecracker and some of the work that we have done and are continuing to do to provide really strong isolation between functions using hardware virtualization. Thank you very much. Oh, sorry, before I say thank you very much, if you're interested in learning more about serverless, we offer a wide variety of training at all kinds of levels, so go and check out aws.training. Thank you very much, and please fill in your surveys.